we have to live with it now. So thanks for the introduction. And first of all, I'd like to thank Maria and Valerie for considering the MZmine project for this great school. And before I start, I'd like to mention that I'm not the main developer of this software. So MZmine is really a community open source project. And I'm just one of the developers for the last few years. But a lot of work I will show today is mainly done, of course, by Tomasz, the head of the project, but also from people like Steffen Heukeroth, Robin Schmidt, and Roman, but also many, many more people. I will definitely miss a lot of people today. But yeah, just as you know. One more disclaimer, I'm currently employed as a software engineer at Bruker Daltonics and develop there the Metaboscape software solution. But the work I showed today was mainly done during my PhD, which I did in analytical chemistry. So what's the scope of this presentation? I will give you a brief overview about the history of MZmine. Then I will give you a short theoretical approach how LC-MS data mining workflow should look like. But the main time I want to spend on a live demo where we can do data mining in MZmine for various data types. So not just liquid chromatography, also other techniques. And then I want to focus, of course, on the annotation of lipids. So the first version of MZmine was already published under the guidance of Matteo Resic in 2006. And as you can see here already, that really visualization was always an important part of the MZmine toolbox. So in general, this was a data pipeline to process profile data from high resolution MS instruments. And it was already then written in the Java programming language, which makes it platform independent. So you could compile it on Linux, Mac OS, and also Windows. So the software got a huge update in 2010 by, here you can see Tomasz Pluskal, who is still the head of this project. And Tomasz has a background in computer science, and he completely changed the code base to a modular framework. So what does that mean? We have the MZmine core, which basically was left untouched by other developers. And other open source developers then can simply add modules to the software. So for example, if I, as a developer, say, okay, I have an idea for an identification or visualization module, I can just add that module and I will not break the rest of the software. With this development, MZmine was really capable of becoming a real open source project. And as you can see, the last publication of MZmine 2 is almost 11 years ago now, but there was still a lot of development going on. And today I have the honor actually to show you a sneak peek of current developments for the upcoming MZmine 3 version. So you will today get to see the early alpha version, and I'm pretty sure the software will crash at least once I show you this. But anyway, let me just briefly show you something about what's going on in the last 11 years towards MZmine 3. So a lot of research groups were taking part of the MZmine project. So here on the left-hand side, you see a lot of papers from the DO lab, and they have integrated and published mainly feature finding algorithms for MZmine. In the middle, you can see a publication about feature-based molecular networking. MZmine is used for the general data processing, so you can use MZmine to directly connect to GNPS. There's also tools from Robin. Robin has developed to directly submit MS spectra to GNPS, so it's closely related to the GNPS project. And also like to mention that over the past years, we have a lot of students working for the MZmine code base funded by the Google Summer of Code project. And we recently also published the latest developments of MZmine in a book chapter. And here on the right-hand side, you can see some publications I was involved in, which relate to the improvements in MZmine for lipid identification or annotation. So I've developed some visualization tools, some rule-based lipid annotation stuff, similar to what Hiroshi has shown today. And together with Robin Schmidt, we also implemented spectra matching in MZmine, which also makes it available for GC MS workflows. With this slide, I like to show you where you can find MZmine. You can find it online at mzmine.github.io. And you can simply download the latest release version of MZmine 2 there. And it's really easy to start it. There's no installation needed. You can run it on all the three mentioned operating systems. But if you are more interested to check out the code, I highly recommend to check out the GitHub space. You can also check the code base for MZmine 3 there already. And if you're really interested to contribute to the project, I highly recommend to contact me or Tomasz or anyone from the project, and we can invite you to the MZmine Slack, where we discuss future developments of the project. And one last commercial slide. Tomasz is now a professor in Prague, and he has an open position for a PhD or a postdoc who can full-time work or mostly full-time work on the MZmine project. And I highly recommend that that opportunity. During my PhD, I had the pleasure to work with Tomasz, and he actually taught me a lot about software development, and I really recommend this as a great opportunity. So let me just briefly explain the theoretical data mining workflow in MZmine. So we always start with importing the raw data. But before that, we can think about if we want to convert the raw data. So we have, of course, different vendors. And MZmine supports Thermo, Waters, and most recently Bruker native raw files, but also open formats such as MZML and MZXML are supported, and many more. The general workflow in MZmine always starts with processing each spectrum of each raw file, and we call that mass detection. So we create mass lists or process those spectra, and with those mass lists, we then create chromatograms, or let us say a big list of chromatograms. And in this particular example, you see a chromatogram or an extracted ion chromatogram can, of course, have multiple eluting substances to at different retention times. So therefore, they are most likely different compounds. Therefore, we have to deconvolute those chromatograms. In this case, it means we have to cut those into individual features, so that each feature really represents one molecule. And also MZmine comes, of course, with the opportunity to analyze more than just one raw file. And for that, we can batch process all together and then bunch it up in a so-called aligned feature list. And with those results, this final feature list, we can then use for annotations, visualization, or for export, or export them and use them, for example, in other tools like MetaboAnalyst. So this is just a backup screenshot in case MZmine fails. So I just jumped to MZmine 3, and I hope you can all see the software now. So I already have imported one raw file here on the left-hand side. And you can do that by selecting the raw data methods menu, raw data import, and here you can see all the supported raw data formats. I'm currently having here a reverse phase chromatography data set from a lipid extract of SRM 1950. Here you can see early eluting lysolipids, and in the middle of the chromatogram, oh, it's a bit slow, I see. In the middle of the chromatogram, we have phospholipids, and at the end of the chromatogram, we have unpolar triacylglycerols. So as you can see here, the plots are interactive. If I click into the base pre-chromatogram, I can see the scan event here on the right-hand side, and also get an extracted ion chromatogram for the most intense signal. And I can also browse through each scan event, and that's really important to, for example, determine the noise level of the instrument. So why is determining the noise level important? That's because in the first step of the data processing, which is mass detection, we have to exactly define that. So this pattern here, selecting a module and then open up a set of parameters, will occur now a lot of time. And I will not explain every parameter here in detail. I just want to show you the capabilities. So what we do here now is we have to process each scan event, so each mass spectrum. And most importantly, we have to check the correct mass detector or the correct algorithm. So MZmine can process profile and centroid data. In this case, I have centroid data, so I just use that one. And this one basically has one parameter, which is adding a noise level. And we always have this preview functionality here. So here you can see the first scan event, and all signals in blue are now filtered out, and all in red are considered for the mass list. And those later will be then used for the further processing steps. I will just cancel this because I already done the processing just to save some time. With those mass lists, we can then start creating our first feature list, or better say, a list of chromatograms. If you now click here on feature detection, as you can see, we have support different types of data. And I just want to show you how LCMS data processing works. Here again, open source software, we have different algorithms from different people. I highly recommend to use the first one here, the ADAP chromatogram builder from the Do Lab. And here you also see a disclaimer that there's a publication out there just for that particular implementation of that algorithm in MZmine. So please give also those people credit who developed this if you use it. So the chromatogram builder works quite easily regarding the parameter input. You just have to tell the algorithm how many data points the chromatogram at minimum should have, and then you define some thresholds, which signals you want to have in the chromatogram, and you have to give it an extraction window. If we run that, we will obtain our first list. I will just quickly sort this by intensity, and you get a lot of information. You get a preview for that for each M/Z value at a specific retention time, as you can see here. And what we still see here at the moment is, of course, that we have ion traces with multiple eluting compounds. So we have to deconvolute those. And for that, we have different algorithms again. And in the feature detection menu, we have chromatogram resolving algorithms. Again, many options. I personally like the local minimum resolver. And this one needs a few parameters as input, but similar to the mass detection algorithms, we here have, again, a preview which visualizes what the algorithm is actually doing. So let's just jump to the feature I just highlighted. This is that mass here. And let's see how the algorithm performs for that feature. So that is MZ782. Yep, a lot of features. What is it? 0.57. And with those settings here on the left, we currently would get 4 separated features, and one has to be quite careful with those settings. For example, if I change this parameter, I would also pick the tailing of this peak, and you would recreate 2 more features, which are just the tailing of this big feature here. So this needs a bit of, I would say, experience, but I recommend to take like 5 or 10 chromatograms where you know these are real features, and then also check out some chromatograms where you know this is not a peak, this is just noise. So you have to then check if the noise is picked or not. And after the deconvolution algorithm, we will get a new feature list, which will then appear here. I will again sort for intensity. And now you can see we really have nicely separated individual features. Some may still show multiple compounds, so we should revise or revisit our settings. But there's always a trade-off, I would say. So with this list, we could already start an annotation workflow. The last step I would highly recommend is to remove 13C isotopes. We also have then a lot of feature list methods here where you can find that one. In the isotopes menu, we have the isotope grouper. And this algorithm basically searches in a retention time window for the specific delta of monoisotopic and 13C 13C carbon. And after that, those features will not be removed. They will just be grouped. So before deisotoping, you can also click, make a right click on the feature list and check the summary. We had like more than 5,000 rows. And after that, we will have about 3,000 in this case. And if I open this one up, I can show you with the right click here. We can check now the isotope pattern. So the isotope pattern here is now stored in yellow. You can see that it's stored in that particular feature list row. And also in that step, the charge is determined as well based on the distance of the isotopic peaks. Okay, what I'm actually showing you here is not just LCMS data, it's actually ion mobility data. And a lot of work from Steffen Heukerott was done to implement this also in MZmine. And if I now go back to the raw data file, I can show you that what we were seeing here is just the sum of multiple TOF scans separated by mobility dimension. And we can now have this nice ion mobility raw data overview in MZmine, where we can check this data now in its full scope. So if I, for example, click select one retention time point here, you can see the average of this ion mobility frame, and I can now select here also a signal, and then I will get, it's taking quite some time here, but he will now also draw the ion trace for that specific ion mobility feature. You can see I selected the mass, by the way, 664.6. This should be a cholesterol ester 18.3. We also see here the neutral loss from the side chain. So this in-source fragment here maybe is quite significant for that molecule. And what we can actually see here, we potentially or quite surely have 2 isomers of that specific lipid, which we could not separate by chromatography alone. So looking at the raw data is fine, but now I'd like to show you how to process that as well in MZmine. So basically the steps are quite similar to the LCMS workflow. We do the mass detection, which I will not show again. You then simply select the LCIMS MS feature detection menu. And here we have two algorithms already. And if you check the ion mobility trace builder, you can you don't need a lot of parameters. You just have to tell the algorithm how many data points you want to have at minimum in retention time dimension, and how many data points you want to have in the whole ion trace. And you will then obtain this. I'll just close the other ones to save some RAM. You will then obtain a feature list with ion mobility traces. As you can see here, you now have a chromatogram, but also a mobilogram, and also a projection in 3D. What we can already see here is, of course, similar to the LCMS workflow. We still, of course, have the we need to deconvolute in retention time dimension, but now we also have to do the same thing for mobility dimension. So we apply this algorithm I just showed you here, the chromatogram resolving local minimum resolver, once in retention time dimension. If we done that, can check that feature list. This is this one here. We already have, again, this nice single features in retention time dimension, but it's still possible that we have multiple features in mobility dimension. And for that purpose, we also have to revisit. Here, for example, we have multiple peaks in mobility dimension, and therefore we will redo the resolving, and simply for the dimension we now check mobility, and the rest works similar. But of course you have to revisit your settings. Once we've done with that, we also should do the de-isotoping again, just to make sure. We learned a lot this week about false positives, and just to remove those potentially false annotations. This one I didn't want to show yet. I just want to show you now that we have clean, more or less clean features in ion mobility dimension. So you can see here. Okay, so this is basically the data processing approach. And I know that these are a lot of steps, but Steffen and Robin have invested a lot of time to make things easier. We always had a batch mode in MZmine, but now you can now we have this nice feature. If we check the show feature list summary, here you can see a list of all applied algorithms for that specific feature list. And I can now directly, I can revisit, by the way, all the used settings. So this is stored somewhere. And I can directly send that now to the batch queue. And those files here, I can export, save, and import again. And I can also share it, for example, in a publication, so people can directly achieve the same results as you are reporting. Okay, let's now focus on the lipid identification. We have various options for identification for lipids in MZmine. So here we have this menu identification. You can use MS1 level stuff alone. So you could use CSV files with your own target lists. But we have also advanced tools, for example, spectra matching. And we also have, similar as Hiroshi explained for MS-DAL, we also have a rule-based lipid annotation workflow. And if I open this one, here you can see the lipid maps hierarchy. So we have categories, main classes, and subclasses. And you can change the scope of the lipid classes you are targeting. And you can then dynamically adjust the ranges from carbon numbers in all side chains combined, and the number of double bond equivalents. So double bond equivalent, it's now here, it's still double bonds, it's a mistake. The only other parameters you need is an MS1 identification threshold for the accuracy. And you can then also check this checkbox here. So currently, if I run this now without this checkbox, we would get just annotations based on the MS1 level, which of course is highly dangerous due to isomeric, isobaric interferences. We've learned a lot about this week. So with this setting here, we activate the MS fragmentation rules. We can give another tolerance for the MZ just on MS2 level. And we've implemented an MS score, which is really simple. So this one just shows you in percent how much intensity of all signals combined in the MS spectrum is explained. For example, your MS spectrum has just one signal, and we can explain that with a fragmentation rule, it would be 100. So before I run this, I'd like to show you this table here. So this depicts the database you are about to deploy on your feature list. And as you can see here, you have information on the lipid class, the neutral molecular formula, and the shorthand notation. And here you can also see which ion species are included in the MS rules. And now, for example, for PC, we have in positive mode sodium and N+H, or in negative mode acetate or formate addicts. And we also have here a color coding. So if the status here is in blue, we have no interference expected on MS1 level. In gray, we have possible interference, or if it's orange here, we definitely will have some isomers in our database we currently deploy. So I just checked 3 lipid classes here, PCs, ether, PCs, and PEs. And of course, we have here isomeric interference on MS1 level for the M+H of PC280 with PE 1310, but also from the sodium adduct from the PC, we could have a possible interference with other PC species. And here you can see then the absolute delta on the of those MZ values. Just here on the right-hand side are also the implemented fragmentation rules we are currently using. Here we have, for example, for M+H, we search for a head group fragment, and here's the ion formula of that fragment. This is the 184, for example, just to make it a bit more transparent what we're actually looking for. So, and one new unique feature for MZmine is you can now implement custom lipid classes or fragmentation rules. So we have here now a nice interface where you can define custom lipid classes. And I will just mimic now phosphatidylcholine just to show you that it actually, you can produce the same result as the hard-coded rules. So you don't need a lot of information. So you just have to define the backbone of your lipid. For phosphatidylcholine, it's basically choline plus glycerol. What is it? 6N. And then you have to assure or have to define what type of chains do I expect for my lipid class, for my custom lipid class. Currently, I just support acyl and alkyl chains, so I can add 2 acyl chains here. And then I can add my custom fragmentation rules. So for example, for my custom PC class, I expect it ionizes in positive polarity mode as an M+H. And I know I will have a head group fragment here. And that head group fragment gives me information only on the species level. So just a molecular formula representation of the lipid. And then I can just enter here the formula of that. This is now the formula for the common 184 head group fragment. This is then stored here. Of course, you can again export and save those rules, so you can then just you can share them or just re-import them. Same goes here for this custom lipid classes. And if I now check out the database, it should be, yeah, here's a custom PC class. It's included with the MS rules, and you can check if everything is calculated correctly or if you maybe have typed a mistake or something. If I run this now, we will get annotations directly in this feature list. And yeah, here we are. This menu here now is new. So we get information on the shorthand notation. As you saw with the custom lipid classes, 2 annotation levels are possible. Here the species level, and for this triacylglycerol, we have the molecular species level. You can see which ion or adduct was used for the annotation, information on the neutral formula, as well as the accuracy on the MS1 level and the MS score. Multiple annotations are possible, and here we should, I didn't run it. If I will run it now again, we should also get the custom PC class here if I did everything correct. Let's just try it. Identification. Here's the custom rule. I will deactivate the rest. Run it. Fingers crossed. And here it is. I typed everything correct. You also get information on which signal was actually matched. So here in orange are matched signals, in blue are not matched signals. And if you right click and show matched lipid signals, you can get, we'll see this spectrum a bit bigger. Actually, we should have a label here that indicates that this was the active fragment. This is currently broken, I just saw. And yeah, this is a nice clean MS spectra from a timsTOF parsev scan. We just see here a huge signal for the precursor and the characteristic head group fragment for the of the choline. Okay, where are we time-wise, Maria? How much time do I have left?
We actually have quite a lot of time, so you can go for another 10 minutes if you wish, but there are also some questions in the chat. So.
Okay, then I will just show a few more features. Some nice plot Steffen just implemented is an overview of all your annotated features in the mobility dimension. So I just I just selected all annotated features, and now I've plotted all mobilograms in this overview. So here you can see the mass to charge ratio against the mobility. And this plot, of course, is interactive. I can just select one feature here and can revisit the chromatogram here and also the mobilogram. And I also get the most intense MS scan. So I can just use this to review my data. And the other thing I like to show for visualization, of course, are the Kenwick mass plots. We have in MZmine as well. So doing this too fast. So we have the visualization menu, where are a lot of possibilities to visualize raw data and to visualize feature lists down here. And the Kenwick mass plot is one of those possibilities to display feature list results. What is the Kenwick mass plot, by the way? Here we redefine a repeating unit and redefine the exact mass of that. So in a classical Kenwick mass plot, we have we redefine the mass of CH2 to exactly 14 instead of the UPAC mass 14.001 something. This has now the effect that we will see lipids on horizontal lines which do differ in the number of carbon atoms in the side chain. This plot is multidimensional. We can display, for example, the retention time in form of a color scale, and we can also use the bubble size to display further features of the feature, characteristics of the feature. for example, the intensity. And if I now plot this, you get this nice Kenwick plot here. And here are the triacylglycerols. You can see that they're eluting very late at 17 minutes. You can use those colors to revisit your chromatography and check if you have false positive annotations. And you can, again, this is all interconnected. You can also get an overview of that particular feature. So here we see, interestingly, for that TG, we also should have another isomer maybe here eluting a bit earlier in chromatography dimension. And you get an overview here again with the MS1 scan and most intense MS scan. Okay, since we have a bit time left, I'd like to show you the next big thing in MZmine. I already showed you that we now are able to process ion mobility data, but we actually are also now, or we plan to support imaging data. So I would just quickly show you, how you can process imaging data now in MZmine. And here I just have a really small batch. I import a raw file, I do mass detection, and then I use the image builder. And here you can see the raw file is already imported. If I double click on it, I can check ion traces for the image. So if I check the range from the min to the max, I of course see all ions. And you can get this image here, and you can then browse each pixel and investigate the spectrum for each data point or pixel here. And we already have done the mass detection and the image builder here in the batch mode. So we already should have a feature list right here. And I'll just quickly sort again by intensity. And we will now have images directly created for all these different mass to charge ratios. Okay, I think this was a lot of input. So I think I should stop here and we should maybe focus on the questions. By the way, Tomasz Pluskal is also in the audience, I think. And maybe he can also join the discussion if he wants to. And I again want to thank you all for the attention, and thanks for inviting the MZmine project.